Right, so undoing the chain rule is the technique we look for first. For given a rate function, we're going to write closed form. So does it have that form where you can write it as a product of two things? And we'll get here eventually. All right, so does it have that form of this is the form you're looking for undoing the chain rule. Don't copy. Okay. Are you listening? Or are you just copying down the board? So always make sure you're doing active note taking, not just copying stuff down. In fact, I'm going to get it off because you guys. It's... Okay. So right. So the undoing the chain rule was this. You're looking for functions, rate functions that are like this. And you're focusing on this part, right? And if it qualifies if your other part is the derivative of the inside, right? If that qualifies for undoing the chain rule. So that's that pattern we're looking for. Okay, and then we said we did undoing the product rule last time. We said undoing the chain rule doesn't work, and we follow that technique of undoing the product rule. So now the next thing we're going to do is for rational functions. What's a rational function? A rational function is a rate of change function that is of this form here. So rational functions look like this. One polynomial divided by another. So I'll call it nx for numerator, d of x for denominator. Those are both polynomials. What are polynomials? Polynomials are of this form. Coefficient times x to a power. Whole number powers, or counting numbers, right? Positive so like quadratics have the highest power 2. That's parabolas or quadratics. Linear functions have highest power 1. Those are example linear functions, quadratics, cubics. Those are all examples of polynomials, and they all have this form. X to some positive whole value. X to some positive whole value. The sum of those, right? Summing up those terms. So each one of these is a polynomial. The numerator is a polynomial. The denominator is a polynomial. Square roots are not polynomials. Fraction exponents or negative exponents are not polynomials. It has to be positive whole numbers for these exponents. Those are what polynomials are. Yeah, no square roots, no negative exponents. Okay, so if we've got a rate function like that, here's what we do first. First we look at the degree. The degree is what the highest power of x that you have. If the degree of the numerator is greater than or equal to the denominator, we're going to begin by long dividing. Long division first. And sometimes that's enough just to do the trick. The long division will give us something that we can do with previous techniques. So let's see an example of that. So here's one. So here, polynomial, 2x squared. Even though it's just one term, that's fine. X plus 1. Those are both polynomials. And here we have that case where the numerator is, the degree is greater than the denominator. So what we can do is, can start by long dividing. And you long divide polynomials the same way you long divide numbers, just like in learning in grade school. So we go x plus 1. And then we're going to write a space for every power of x. So we have 0x to the first, and we have 0. So leave a space for every power of x. And if it's not there, then it has a 0 coefficient. Same with this. If this were x squared plus 1, it'd be x squared plus 0x plus 1. And then remember how you long divide. You ask, what am I going to multiply x plus 1 by to get 2x squared as my highest power? So what am I going to multiply x plus 1 by to get 2x squared? 2x. And since it's 2x, it's going to go in the x column, above in the x to the first column. My 2x times x plus 1, we bring it down here, 2x squared plus 2x. It should feel just like long division that you did in grade school or pre-algebra, whenever you did this. And then we subtract, and when we subtract, that left-hand column will be 0 because of choosing 2x, right? So we're going to subtract, and when we subtract, we'll get 0, and then what? Minus 2x. And then we ask again, what do I multiply x plus 1 by to get minus 2x as my first term? I'm going to multiply this by to get minus 2x. Minus 2, right? Minus 2. So that's a constant. It'll go in the constant column, right? It'll go in the constant column. So minus 2 times x plus 1 is going to be, oh, sorry, we didn't bring down the 0. So you got to remember, before you do that, you got to bring down the 0. Forgot to do that. All right, then minus 2 times x, minus 2x, minus 2. We're going to subtract that. So we'll have remainder of plus 2. So now we have a way, now that we have the quotient and the remainder, we have a way of rewriting this. So this is the same as now. Integral of, what, 2x minus 2, the quotient, plus the remainder over the divisor. Remember this? So this original rational function that I was given is equivalent to that rate function, 2x minus 2 plus 2 over x plus 1. Oh, we forgot to ask the important question before we started. What was the question we should have asked from the very start, before we started? Yeah, is it undoing the chain rule? Is it undoing the chain rule? Okay, no, definitely not. Okay, how could it be undoing the chain rule? What one little change could we make so that's undoing the chain rule? Always ask that question. So what one little change could we make in here so undoing the chain rule would apply? He wants x cubed in the denominator. That's right. If this was a 3, we'd have it. 2x squared over x cubed plus 1 would qualify for undoing the chain rule. Why? Because the 2x squared is essentially the derivative of x cubed as the right powers, right? But we didn't have the x cubed. So then, and this is a rational function, so we can use this technique. Okay, so now continuing with the problem. So now, can we do this? Did long dividing help? Definitely, right? So this is piece of cake now. 2x, antiderivative. No, x squared. And then antiderivative minus 2. Minus 2x. And then 2 over x plus 1. Natural log, right? That's x plus 1 to the minus 1. Absolute value. And then what? All possible accumulation functions starting from any a means, which is, remember, that's our minus f of a. Questions on this example? So sometimes just doing the long division, that takes care of it. It gets us an equivalent rate function that we can do. So, but you always got to check for that first. Okay, so now, sometimes though, this fraction that you get will still be not simple like ours was. The 2 over x plus 1 is easy, but maybe you end up with another, this is another rational function, right? This is another rational function where n is less than d, right? N is less than d, and it's not immediately apparent how to do it, okay? So that's what we're going to work on next. Questions on this long division example? Anybody have a question? All right, so if n is less than d, and also, so we have a rational function. Is it one polynomial divided by another? Are those two polynomials divided? Yes, that's the first qualification. N is less than D now. True? Yeah, degree of the numerator is 1, degree of the denominator is 2. Last qualification is that the denominator can be written as some kind of product, right? So some polynomials factor into product of factors, others don't. In order to use this technique I'm about to show you, this denominator has to be able to factor. So does it? So again, blast from the past, right? Factoring quadratics, right? Factoring quadratics. Does it? 2x and x. So we need product of -1 and sum of -1. Can I get it? Know what I'm doing? Done this before? So this should be 2x, what? Plus 1 and x minus 1. That gives me a product of -1. My middle term will be minus 2x and plus x. Gives me minus x. Works. Okay, so this qualifies for this new technique I'm about to show you. Okay, it's not undoing the chain rule. It's not, undoing the product rule could get very ugly here. Maybe it'll work eventually, but want to avoid it. So really, this is a perfect candidate for what we're about to do. And so what we're about to do is, the idea is that you can think of this as the sum of two fractions, where we had two fractions. When we added them together, we got a common denominator and made it all one fraction. So we're going to decompose this. So it's like going backwards from adding fractions. Finding the two fractions that, if added together, would give me that. So what would my denominators be such that the common denominator would be this? Remember how to find a common denominator? You end up multiplying them, right? So I can rewrite this as something over 2x plus 1 and something over x minus 1. So remember, so think about this. When you add these together, how do you get the common denominator, right? How do you get the common denominator? It's the least common multiple of these two, right? So we would multiply them because there's no common factors there, so we just multiply those together. There it is. There's our common denominator for adding. So the question is, what are the numerators that when we would add them, we'd get 5x plus 1, right? Okay, so is this making sense so far? Any questions? Okay, so let's add them. So how would we add those fractions? What would we do to the first fraction so it's ready for these two to add together? What would we do? Do you remember? You want to multiply the numerator by something? By what?
Well, for A, you want to multiply that by
X minus 1. So like this?
And
Now or later?
let's do it.
Yeah, now. You can't just change it. If you just multiply the numerator, then you just change the value of the fraction. If we multiply by both, then we multiply by 1, and we keep the fraction. Okay? And then what about the second one? So again, my goal is the common denominator. What's the common denominator? 2x plus 1 times x minus 1. So what do I need to finish the common denominator? Right. So that gets me the common denominator, but if I do the denominator by that, also the numerator. So I split it apart into a general form where I didn't know the numerators, but now I'm gonna get ready to add them back together again, right? So I'm adding them back together. And so therefore we have what? 2x plus 1 times x minus 1. Numerator is a times plus. So this is going to help us find a and b. How are we going to find a and b? A and b are such that this, what? Has to be what? That's right. It's got to be that. Did you catch it? Does this make sense? So that numerator, a times x minus 1 plus b times 2x plus 1, has to equal 5x plus 1 in order for a and b to be correct. So we're looking for a and b that makes that equal to that. All right, so we got a times, I'm going to multiply it out in this step. Is that okay? It's just the numerator now. A times x minus a plus 2bx plus b has to equal 5x plus 1. Okay, so look, so we have a linear term and a constant term. So the linear term on the left has to, the coefficient of the linear term, the x to the first, on the left has to equal the coefficient of the x to the first term over here, and then the constant on this side has to equal the constant over here. So that gives us a couple equations. So linear terms, let's do red here. So what are our linear terms? Linear coefficients. A and 2b. And then, what's our constants? Oh, sorry, so let's, and we'll say that's our 5. And then, what our constants are? Minus a and plus b. So we're going to match those up. The coefficients of x on the left have to add up to 5, and the constant terms have to add up to 1. So that means that, what, minus a plus b equals 1, and a plus 2b equals 5. And now we got two equations, two variables. And you can solve this however you want. There are multiple methods for solving systems of equations, right? This is two equations, two variables. So there's substitution, there's elimination, matrix method, whatever you want. Any way you can get a and b. Any way you can get a and b, that's what we're doing now. So this one's just totally set up for elimination, right? All I have to do is add these two equations together and see what happens. A's just go away, right? You got a and minus a. So this is easiest, I think, with elimination. Just we're going to add a's, add b's, add constants, and we end up with 3b equals 6. Therefore, b equals 2. And then we can use either equation with b equals 2 to get a. So the second one, b equals 2. So -1. So a is 1. And so now we can rewrite our original problem, or this, it's complicated. So then this, which is equal to the original problem, we know what a and b is. So we can come down here like this. 1 over 2x plus 1 plus 2 over x minus 1. And now each of those are individually easy, right? So we get 1/2 natural log 2x plus 1 plus 2 times natural log x minus 1. Yeah. You tell me. Think about derivatives. It's all about derivatives. It's all about derivatives. Take the derivative. Take the derivative. If you don't want the 1/2, then take the derivative. It's all about derivatives, right? What happens when you take the derivative? That's all. The whole ball game.
Oh, and inside, right? Okay.
Chain rule, right? Undoing the chain rule. Yep. Okay, questions on this then? So this is called partial fractions. We're decomposing a single fraction into two and then solving for those numerators and then rewriting it. So this sum of fractions is equal to the original fraction we were given. And then that's doable. Okay, so tell the person next to you. What's the meaning of that expression right there? What's the full meaning of that expression? Tell the person next to you. Go. Okay, Dustin, what do you think? What'd you say? What'd you guys talk about? What's the meaning of that expression right there?
You were thinking that it was still the net accumulation.
Okay, it's a net accumulation function. Good. So it can be more specific. So give me some details about that net accumulation function.
That it's the net accumulation when the rate of change is 1 over 2x plus 1 plus 2 over x minus 1.
Okay, or even better, it's when this is the rate, right? Yeah, that's good. That's true because those are the same. But let's go back to the original problem. The rate is that. Okay. Anything else? Starting from where?
Starting from f of a, which is c.
So starting from a. So starting from but here it's any value of a, right? So yeah. So this is the whole family of functions, net accumulation functions with that rate up there. The whole family meaning it can start from any value of a, and that's what c determines, right? The plus c is determinant of your starting value of a. So that's what you should have talked about, right? Okay, let's do a harder one. Oh, come on, that was easy. Maybe not for the first time. So, 3 qualifications for partial fractions. First is it a rational function? Is it a rational function? Well, actually, we should ask, is it undoing the chain rule? Is this undoing the chain rule? This is 3 things multiplied together. It's not fitting the bill here. Okay? So undoing the product rule, unlikely. Unlikely for undoing the product rule. So we've got, do we have a rational function? It's a polynomial divided by a polynomial. Yes. Is the degree of the numerator less than the degree of the denominator? Degree of the numerator is 2. Denominator 3. Right? If you multiplied all the x's together, you'd have x cubed as your first term. Lastly, can the denominator be written as a product of factors? It already is, right? So it already is. So we're golden here. So now we're going to write this as, so possible, we've got to think about, and there's actually 3 possible denominators that when you add together, you get that common denominator. So the first one is x minus 3, x minus 2 But there's another possible denominator we could have that these don't cover. And that's x minus 2 squared. So these are all possible denominators that could be in the mix that when you add these fractions together, you get that. You got to include that x minus 2 squared. So if it were x minus 2 to the 5th, we'd have x minus 2 squared. We'd have a denominator x cubed to the 4th to the 5th. You'd have every possible power of the x minus 2. They're all possible denominators that contribute to this common denominator. Okay? So then we're going to have A, B, and C. All right, it won't always be just constant A, B, and C. We'll see in the next problem when it's not. But in general, we've got, these are all linear factors. X minus 3 is linear. X minus 2 is linear. And this is still x minus 2. It's still a linear term. It's squared, but it's still considered a linear term, just to a power. So whenever you have a linear term in the denominator, you use a constant in the numerator. All right? And we'll talk about more of that on the next example. Okay, so we're off to the races here. So if we were to add these together, I'm going to do it here. Let's do pretty green here. So what would I need to multiply this one by to get the common denominator? X minus 2, not cubed. There's only 2, right? Right? And then what am I going to need to multiply this by, this second fraction, to get the common denominator? So I've got a single x minus 2, and I got to get the common denominator. So what do I need? I need an x minus 2, and I need an x minus 3 in this one. Yeah, sorry.
Okay.
And then this last one, C. What do I need to multiply this fraction by to get the common denominator? Just an x minus 3. Make sense? So I split it apart, I get all the possible denominators, then I look at each fraction and I ask what do I need to do to each one of those to get the common denominator, and then I got to do the same thing in the numerator. So now this whole numerator now, so we know we're going to add the fractions together, and we're going to just add the numerators. When we add those numerators, we're going to get x squared plus 1. So let's write that out. So A times x minus 2 squared plus B times x minus 2, x minus 3 plus C times x minus 3 equals x squared plus 1. So we'll do x squared plus 0x plus 1. So we keep in mind that we have still have a linear term, but it's going to have a 0 coefficient. So this is coming from this, right? So that numerator added has to be x squared plus 1. I didn't do that math and say it's equal to that. We're about to do this math over here. But whatever that sum of numerators is has to be x squared plus 1, our original problem. Here we go. Fast. Ax squared minus 4ax plus 4a plus bx squared minus 5bx plus 6b plus cx minus 3c equals x squared 0x plus 1. Did I make a mistake? Did I do that right? Please check my work. I think it's right. Here we go. So now this time we have a quadratic coefficient, a linear coefficient, and a constant. So we got the coefficient of x squared, coefficient of x, and a constant. So we'll do quadratics first. So quadratics, red triangles. I think that's it for that, right? And what is this? This is a 1, right? And then linear terms, do blue circles. Linear terms, minus 4a, minus 5b, and c. And that's going to be 0. What do you think? Orange or brown? Or violet? Violet. Squares. It's like lucky terms, right? 4a. That's not food, by the way. It's not food. Okay, 4a plus 6b minus 3c plus 1. Cinnamon Toast Crunch, that's food. Okay. All right, so we got our red equation. A plus b plus 0c equals 1. So I'm just kind of doing this. I'm going to let you stop me if I lost you. So please do. Please stop me if I'm losing you here. Minus 4a minus 5b plus c equals? That's my linear coefficients, my blue circles. Then 4a, 6b, some of you have been waiting for algebra all semester. It's your lucky day. It's just pushing the symbols around. Okay, so now we got 3 variables, 3 equations. So so again, you can use elimination, but it's going to take like 2 layers of elimination or substitution or a matrix method, whatever you've learned that you want to do. So one thing I see here is we already have C eliminated from equation 1. So if we got C eliminated from equations 2 and 3, then we can combine that with equation 1. To me, that looks like a good strategy. So how do I eliminate C from equations 2 and 3? Multiply by positive 3, right? If I multiply by positive 3 and then add these two, it'll get rid of C. I'll be left with something of A and B, which I can combine with the first equation. So negative 12a and 4a looks like negative 8a. Negative 15b and 6b is negative 9. Check my work. And the 3c. And then 0, 1. Agree? Agree with the math? Okay. So now let's for something new. So now we're going to combine these two. And let's do a substitution for that. So what is A equals what? A equals 1 minus B. So let's plug in 1 minus B for A. So since A is 1 minus B, we'll put 1 minus B in for A and solve for B. Minus 8 times 1 minus B minus 9B equals 1. So that gives me negative B on this side, minus 8 check my math again here. So negative b equals 9. So b, I think b is negative 9. I don't think that's right. Did I blow this here somewhere? That's what you got? I just remember this having fractions for answers, but so what would a be? 10? Okay, and then c, we could use equation 2 for c. So in equation 2, we get minus 4, so minus 40 plus 45 plus c equals 0. So I think c is negative 5? No. Yeah, right? So then we go back to this. So now you plug your a 10 in here, negative 9 in here, and negative 5 here. So then we're going to have what? Natural log, let's see, but 10 natural log, I'm going to write the answer down here. 10 natural log of x minus 3. Did I make a mistake? If I did, please stop me as soon as you think I made a mistake. Negative 9 natural log of x minus 2. All right, in this last one, I'm going to have negative 5 over x minus 2 squared. Is that going to be natural log? No, that's just power rule, right? That's not to the minus 1. It's to the minus 2. So this is power rule. So I'm going to have minus 5 times, it's going to be x minus 1 to what power? Raised power, right? Negative 1. And then we're going to have another negative 1 for that. X minus, yes, thank you. Right. And then I need another negative 1 for the negative 1 exponent. So that becomes plus 5, plus c. I just need to start the next one. That's why I'm hurrying through this at the end of this one. But please, if I lost you, please ask. Do you agree? Any questions? Okay, you can check the video if you're still thinking or writing. So last one, I just want to set it up. Last chance, going, gone. Last one. Okay, this fits the bill. 10 is considered a polynomial, that's fine. It's just a constant, but that's fine. And then we need to factor that. Does that factor? Yep, x times x squared plus 4. So this qualifies for what we call partial fractions, decomposition of fractions. And so here, it's something that's a little bit different here because we have a true quadratic term down here. So yeah, we're going to have x and x squared over 4, x squared plus 4. And this is linear, right? X to the first. Linear means constant. But a quadratic, this is a true quadratic polynomial here. What we have in the numerator has to be 1 degree less than that. That's where we're getting constants because it's 1 degree less than linear. So if this is quadratic, 1 degree less is to the first. So we're going to have bx, but then also plus a constant. So when you have a quadratic term that's truly quadratic, the last example was not, you need bx plus c. And then everything else is the same. But now you're solving for 3. You're still solving for 3 unknowns to redo your problem. So solve for a, b, c. And everything else in this problem is the same as previous problems. So when you have a linear denominator factor, you put a constant in the numerator. When you have a quadratic denominator, you need a linear, full linear term, which is bx plus c. If it were cubic, it would be bx squared plus cx plus d. Okay, so remember you'll have 2 WebWorks due Monday at 5. 2 WebWorks due Monday at 5. Yeah.
Are you able to post the solution to this online?
Yeah, sure. I'll put this. I'll tag video from last semester. Yeah.